Okay, we move on to design of alignment. So you have to take note that the alignment of a highway is composed of vertical and horizontal elements. So when you talk about vertical alignment, that includes straight, or we are referring to the tangent, highway grades, and the parabolic curve that connects these grades. When you talk about horizontal alignment, it includes the straight, which is talking about the tangent section of the roadway and the circular curve that connects their change in direction. Note that the design of the alignment is dependent primarily on the design speed selected for the highway. So, which means that when we design a highway, for a certain design of a highway, we consider the design of the alignment, which is dependent on the design speed. The least cost alignment is one that takes the form of the natural topography. So, which means that for a certain highway design, to have a less cost of the design of the alignment, so we have to take the form of the natural topography. It is not always possible to select the lowest cost alternative because the designer must adhere to the certain standard that may not exist on the natural topography. So it's not always that we have to consider the natural topography in the designing of the alignment so that we could have a least cost on the design of the alignment. The designer must consider the adherence to the certain standard that may not exist on the natural topography. It is important that the alignment of a given section has a consistent standard to avoid sudden changes in the vertical and horizontal layout of the highway. It is also important that both horizontal and vertical alignment be designed to complement each other, since this is the result with a safer and more attractive highway. It is also important that both horizontal and vertical alignment be designed to complement each other, since this is the result with a safer and more attractive highway. So one factor that should be considered to achieve compatibility is the proper balancing of the grades of tangent with curvature of horizontal curve and the location of the horizontal and vertical curve with respect to each other. So, for example, if a design that achieves horizontal curve with a large radii at the expense of steep or long grades is a poor design. So this is an illustration. This is a table showing to us the recommended maximum grade. So based on the table, it shows that we have the type of terrain, and with respect to the type of terrain, we have the rural collectors or the design speed for the rural collectors with respect to the type of terrain. And this one is a table showing to us the design speed for urban collectors with respect to the type of terrain. So we have here the specific grades, and you have for rural arterials design speed. We have also the rural and urban freeway design speed and the urban arterials design speed. So dependent on the type of terrain, you just have to refer what value of the design speed you are going to consider. We move on to vertical alignment. So when we speak about vertical alignment, it specifies the elevation of points along a roadway. So this elevation of this roadway points is usually determined by the need to provide acceptable level of driver safety, driver comfort, and proper drainage from rainfall runoff. So we have to take note that when we speak about vertical alignment, it has something to do with the elevation of points along the roadway. And we have to take note that this elevation is in the roadway points is usually determined to provide acceptable level for the driver's safety, driver's comfort, and proper drainage. A primary concern in vertical alignment is establishing the transition of roadway elevations between two grades. This transition is achieved by means of a vertical curve. So that vertical curve can broadly classified into crest vertical curve and sag vertical curve. So we have two types of vertical curves. So you have the crest vertical curve and sag vertical curve. So, in our figure, figure 3.3, you have the illustration for the two types of vertical curves, which has the vertical crest vertical curve and sag vertical curves. So this is an illustration for the two types of vertical curve. We have the crest vertical curve and the sag vertical curve. So in our illustration, we have our variables identified on our crest vertical curve and sag vertical curve. You have your G1, which has the initial grade of the roadway. You have the G2, which has the final grade of the roadway. Then we have our PVC, which has the initial point of the curve. PVT is the final point of the curve. And we have PVI. PVI is the intersection between the two grades. The two grades that we are referring is the final grade and the initial grade. And of course, you have A, which is the difference between our initial grade and the final grade. Then we have our variable L to represent the total length from PVC towards PVT. And of course, from PVC towards PVI, that is L all over 2. So we have the difference here of the illustration, how it is being identified for crest vertical curve and sag vertical curve. For vertical curve fundamentals, in connecting roadway grades, we are referring to the tangent with an appropriate vertical curve, a mathematical relationship defining elevations at all points along the vertical curve is needed. So for this one, for the vertical curve fundamental, we are trying to use the concept of the parabolic function, which is noted to be suitable because of other things. It provides a constant rate of change of slope and implies equal curve tangent. So the equations that you will be using, of course, you are familiar with this, which is from your analytic geometry, which is in general form of the parabolic equation. So we have here our equation for the vertical curve, which is equivalent to y is equal to ax squared plus bx plus c. You have to take note that our y is the roadway elevation at a distance x from the beginning of the vertical curve. Then our x is the distance from the beginning of the vertical curve in station. And our a and b, those are coefficients. And C is the elevation of PVC. Of course, we know that PVC is our initial point of the roadway. So our X here is equal to 0. So for us to define the value of the coefficients A and B in our parabolic equation for the vertical curve, so we take the first derivative of our parabolic equation. So if we're going to have the first derivative, this is our first derivative, which has d of y all over x equal to 2ax plus b. So at PVC, wherein at PVC our x equal to 0. So if we try to substitute that one to this equation, so our b now will be equal to dy all over dx, and actually this equation is equal to g sub 1. You have to take note that our g sub 1 is the initial slope. So if we take the second derivative from our equation, from this equation, if we take the second derivative, that will be equivalent to d squared y all over dx squared equal to 2a. So the average rate of change of slope, which is d squared y over dx squared, is equal actually to g sub 2 minus g sub 1 all over L. So if we try to substitute the value of g sub 2 minus g sub 1 all over L to this equation, we obtain the equation to be g sub 2 minus g sub 1 all over L is equal to 2a. And if we try to solve for a, we get the value, which is a is equal to g sub 2 minus g sub 1 all over 2L. So we have now the value for our coefficients a and b for our parabolic equations of the vertical curve.